So the equations that we're going to be looking at are similar to the ones that we did for the arc sine and the arc tangent and the arc secant. So these typically involve some variable x or something like x squared. I mean, it could be x to the fourth. That's x squared squared. And it involves some constant term. And the result ultimately ends up being something relating to a. So if we have a squared in the original one, we'll have a squared in the answer. I mean a in the answer. And if our variable part is x, then we have x. If it's x plus 2 quantity squared, then we'll have x plus 2. So when we did these, we based these integrals on the definition of the derivatives. We said the derivative of the arc sine was 1 over the square root of 1 minus x squared, and therefore we said the integral of 1 over the square root of 1 squared plus x squared equal the arc tangent of x. And then we generalized it to a constant a squared instead of just 1 squared. So we're going to have integrals involving these three situations, where we have the square root of a squared minus u squared, the square root of a squared plus u squared, and the square root of u squared minus a squared. U is whatever we decide to use for u substitution. And if you look at what we've already dealt with, here we have a squared minus x squared of a squared minus x squared, so that fits into this kind of situation. Here you may not think it does, but if I would square this, then I would end up with that. So even though sometimes it doesn't look like it fits into these forms, but it does. So let me kind of try to describe how we deal with this. And it kind of, just because of the fact that we've seen things like this before, it involves the arc, well, it involves trig functions, even though the original integral doesn't involve trig functions. Another thing is that the domain of this function is going to be such, the square root has to be a positive number. Therefore, a squared minus x squared has to be a positive quantity. They kind of look like variations of the Pythagorean theorem, so that might not be. So when we use the Pythagorean theorem, we use triangles. It shouldn't be as a huge surprise. So what we're going to do first is we're going to look at this first variation, and we'll look at each one of them. The sound's on here. Turn that thing off. Okay. So if we have a integral involve something like this, we're going to construct a right triangle to use those variables to kind of relate, to do our substitutions. And let me just flip that. The smart board doesn't like having it the other way, but I'm going to flip it left or right, so because I like it that way, just because I'm used to it. So what we do is we define an angle. The angle in the lower left corner here is theta, and this is a right angle. And this kind of form of the integral is going to tell us that we want to use the sine of theta to be the substitution, because remember, this is called trigonometric substitution. So we're going to try to substitute this with some trig functions. So we'll say for integrals of this form, we will use sine theta. And you'll see why in a second. So if I let the opposite side from the angle to be equal to u, and I let the adjacent side equal the hypotenuse equal to A, and I say this is I'm trying to figure out what this unknown is. Let's call it just something so it's not usual. Let's call W. Well, let's not use W because that's close to U. Let's say M. Okay, so the Pythagorean theorem would say m squared plus u squared is equal to a squared. The sum of the squares of the two sides of a right triangle equals the square of the hypotenuse. And if I solve for m, what I would do is I'd subtract this from both sides, so I get a squared minus u squared, and I take the square root, and I get m is equal to the square root of a squared minus u squared. Okay. So that means I can replace that with the square root of a squared minus u squared. And that's why we choose the sign, such that if one of the sides of the right triangle is the u part, and another side, including the hypotenuse as a side, is a squared, then the third side via the Pythagorean theorem is the square root of a squared minus u squared, which is what I'm trying to do. Now, if it's a squared plus u squared, then I'm going to use the tangent. If it's u squared minus a squared, I'll use the secant. I could use the cosine as well, but there's no advantage to using cosine, so we just stick with the sine. Okay. So now that we've defined that right triangle as such, we can say a few things. We can say that the sine of theta, which is equal to the length of the opposite side over the hypotenuse, is equal to u over a. We could say the cosine of theta, which is the adjacent length over the hypotenuse length, is going to be equal to the square root of a squared minus u squared divided by a. The tangent of theta, which is the opposite over the adjacent, is going to be u divided by the square root of a squared minus u squared. And I'm just going to do them all for this time, just so you know. The cosecant of theta, which would be 1 over the sine of theta, is just a over u. The secant of theta, which is 1 over the cosine of theta, is a divided by the square root of a squared minus u squared. And the cotangent of theta, which is the adjacent over the opposite, or 1 over the tangent. I guess I should use that to be consistent with what I'm doing here. So I get 1 over the tangent of theta, and that's equal to the square root of a squared minus u squared over u. So you can see I can define all the trig functions in terms of these, the three sides of the triangle, just using SOHCAHTOA or whatever you want to call it, and the definitions of the others. So the whole idea here is that we're going to take an integral and we're going to use these substitutions plus one more, because we're going to need, in the original integrals, we can replace this with one of those trig functions. The last thing we usually have to deal with is how do you deal with dx or du, depending upon whether it's u substitution or not. And so to do that, we take the first substitution and we solve for u. So u would be equal to a times the sine of theta. So if I wanted to get du, that would be equal to a times the derivative of the sine, which is the cosine, d theta. So I can make, if I'm using u substitution, I can use this to replace du just by taking the derivative of that and then multiplying by d theta, which is the variable, instead of x. So let's just look at an example. So we'll do something we already know what the answer is. Well, no, we're not going to do that one. We're going to do x divided by we know how to solve this one already but we're going to do it this way, another way instead. We could just use direct U substitution, but we're going to use trig substitution just to show you how it works. So what we have is the integral of x divided by the square root of 9 minus x squared. So we could just say u is equal to 9 minus x squared, and du is equal to negative 2x dx. So we could solve it. And the answer, we've done it enough times, it's going to be the square root of 9 minus x squared. Right? We've done that. Because the half from the 2 from the du cancels out with the half from here. I think that's, remember how that works. Okay, but we're going to use trig substitution just to show you how it works. So rather than using this generic triangle, I'm going to use a specific triangle. And again, I'm going to switch it sides here because I can't handle it. Switch here. Okay. So I'm going to let this be theta. The opposite side is going to be x, and the hypotenuse is going to be 3. Because it's a squared minus u squared. The hypotenuse is a, and the opposite is u. U is x. So that means we've already done it. The adjacent side is 9 minus x squared. So that's my specific triangle for this specific problem. So the substitutions we're going to use here are that u is equal to a times the sine of theta. Actually, we're going to say it's not u, it's x in this case. Yeah, so x. So in this case, it's just a simple x because we don't have like x minus 3 quantity squared. If we had x minus 3 quantity squared, we'd do something different. Okay, we'd let u equal x minus 3, and then we do it. But in this case, we can just let u equal x. So x is equal to a sine theta, where a in this case is 3. So that actually, let me go back one step here. If you just use the definition of the sine, you'd say the sine of theta is equal to the opposite over the hypotenuse. And if I solve for x, multiply both sides by 3, I get that. So that's going to be my substitution for this part. So I'm going to use some color coding here. So here I have that substitution. I need this substitution and that substitution now. So the next thing is I take the derivative of both sides here to get dx. So I'll get 3 cosine theta d theta. So that's my substitution for dx. So that goes there. And then the last one is this cosine thing here. So the what I'll say is the cosine of theta is equal to the square root. Well, I can just use it from here. The cosine is the adjacent over the hypotenuse. So the adjacent is 9 minus x squared, and the hypotenuse is 3. Well, the substitution I need is the square root of 9 minus x squared. So to get that, I just multiply both sides by 3. So I get the square root of 9 minus x squared equals 3 cosine theta. Okay, so that's my last substitution. So for this, I'll put that in there like that. So my original integral, which was in terms of x, now is going to be in terms of theta. So for x, I put in 3 sine theta. For the square root of 9 minus x squared, I put in 3 cosine theta. For dx, I put in 3 cosine theta d theta. Then I simplify. So you can see the cosines cancel out, the 3's cancel out. So I get the sine of theta, 3 times the sine of theta d theta. So this 3 is still there. This cancels out with that. That cancels out with that. So I get 3 sine theta d theta. And at this point, I can, it's a simple integral. I don't have to do any trig integration. I just have to use a formula that's in in the book, normally it's the integral of the sine of u, but theta is just a variable, so there's no reason why you can't just use the rule. So the integral of the sine is negative the cosine. So we get 3 times negative the cosine of theta plus c. Just like with u substitution, when we do u substitution, we do the integration. We use the u substitution to get it into a form that we can use one of the formulas in the book. Once we do the integration, then we go back and make the substitution. In this case, it's not quite as easy because we don't have it's not like we're using this substitution here. We have to find the trig function that, or if we don't have it already written down, we'd have to go back here and use one of these definitions. Just use the definition of whatever trig function you need to substitute it back in to get the answer back in the original variable, which is x. So what we see here is the cosine of theta is that. So I'm going to use that to rewrite it, go backwards. So I'm going to take the negative sign, stick it out front, and the cosine of theta is equal to the square root of 9 minus x squared divided by 3. You see the 3's cancel out, and I get negative the square root of 9 minus x squared plus c. And there's your answer, which is what we would have gotten if we had just used u substitution. The reason we got the negative sign was because we had 9 minus x squared. So the negative would have shown up. But we have done that quite a few times, including tests. So it would have been easier just to use u substitution, but it shows that for one thing, it shows all the 3 types of substitutions, for x, for dx, and for the square root of 9 minus x squared. But if I did something like, this is dangerous because you don't know how it's going to turn out, but I'll take the chance. What if I had the integral of x squared divided by the square root of 9 minus x squared dx? So all I've done is I've changed the numerator to x squared. But I can't use, it doesn't fit, it's not going to work for u substitution because if I let u equal 9 minus x squared, du would be negative 2x dx, and I've got x squared in the numerator, not x. So that's not going to work. And it's not going to work with the inverse sign because I have x squared. If I had nothing, if I just had a constant in the numerator, then I could use the inverse sign, but just that one extra x messes things up. So, but I'd still solve this problem using the same substitutions. So let's see what happens. So for x, if I go back to the previous problem, x was equal to 3 sine theta. So I'd have 3 sine theta quantity squared. So that's the x substitution. The substitution here, dx was 3 cosine theta d theta. So that's going to be 3 cosine theta d theta. And I'm going to divide by the square root of 9 minus x squared, which is 3 cosine theta. So that's it. So I have an extra 3 sine theta in the numerator. So let's go ahead and simplify again. So those would cancel out, those cancel out. And what I'd end up with is 9 times the integral of the sine squared of theta d theta. Instead of 3 times the sine of, instead of 3 times the integral of sine of theta d theta, have 9 times the integral of sine squared theta d theta. So the question is how would you solve that? Well, we'd use power reducing formula, which says sine squared theta equals 1, I forget what the formula was. It's either 1 plus or minus cosine of 2 theta. Remember that one? Let's find it on the internet. Power reducing formula for the sine. Yeah, so sine squared is 1 minus cosine of 2 theta over 2. 1 minus cosine 2 theta over 2. So I could do that, and then I can integrate it. I'm not going to integrate. We've seen from the previous section that we know how to do that. So I could do that, and then I'd get whatever the result was. I could then plug it back in. Now the issue is you're going to have 2 theta, and how do you deal with that? We'll come back to do that one, but I don't want to worry about that yet. I just want to. Okay, so let's do another one here. Let's look at the integral of what we're going to do is the one that we know the answer to, which is going to be the arc tangent. So if we had 1 over 9 plus x squared dx. Again, that one is just going to be, we know the answer, but let's use trig substitution to solve the problem. Actually, I'm going to cheat here. I'm going to change it to this. We're going to put x. Okay. Again, we could use u substitution. If you let this be u, then this would be some form of du. So let's make up a triangle. Switch this thing around. Okay, so what I said earlier was, I think I said it. Well, I didn't say it yet, but if you have a form where you have a squared plus u squared, then you want to use the tangent. So we'll do that. You'll see why in a second. So let's say the tangent is the opposite over the adjacent. So in this case, I'm going to let x be the opposite side and the adjacent be 3. And as a consequence, the hypotenuse is going to be the square root of 9 plus x squared, because this squared plus that squared equals that squared. So if I solve for this, it's going to be the square root of this squared plus that squared. And so by using the tangent to define my original triangle, I get something that kind of looks like the denominator here. It's not exactly, but if you square this, you'll end up with that. So what we're going to say is the tangent of theta is x over 3 instead of the sine of theta. So we can solve for x just like we solved for x in the previous one. We get that. So we've got that substitution. Again, we need the dx substitution. So we take the derivative. Dx is equal to 3 secant squared theta d theta. So again, we have to know our derivatives. Before, the derivative over here, the derivative of the sine was the cosine. Here, the derivative of the tangent is secant squared. So that gives me this next substitution. And the final substitution I need is this one. So what trig function you use is the one that involves this divided by that. And why is that? Because I want to really get this term just involves a constant factor. If I used the sine, then I'd have x and this thing. And so I wouldn't have just a constant difference between what I'm trying to substitute and what I have. So what the question is, what trig function is the hypotenuse over the adjacent? So we'll say what trig function is hypotenuse over adjacent. So the easiest way is what is the trig function that's adjacent over hypotenuse, which is cosine. Therefore, hypotenuse over adjacent is the secant. So that's what we're going to use here. So we're going to say the secant of theta is, the secant of theta is equal to the hypotenuse length divided by the adjacent length. And just like before, what we're trying to do is solve for this thing, because that's the substitution we need to make. So we're going to say the square root of 9 plus x squared is equal to 3 times the secant of theta. So let's underline our substitutions here again. So you got for x, we're going to put that in there. For dx, we're going to put that in there. And for that, we're going to put that. It goes there. Okay. So what do we get? We get, so our original integral, which was in terms of x, putting in these substitutions, you're going to have 3 tangent theta. That's x. Dx is 3 secant squared theta d theta. And the denominator is going to be 3 secant theta squared, because what I have in the denominator is 9 plus x squared, and I have here the substitution is the square root of 9 plus x squared. So if I square this, I'll have that. Therefore, I need to square that. So those are my substitutions. So now what do? We simplify, and you'll notice that this secant squared cancels out with that secant squared. Those two 3's cancel out with that 3 squared, and all we're left is the integral of the tangent of theta d theta. So it looks, initially you're thinking, this is getting really complicated. I'm never going to get it. But one thing is we're going to spend a lot of time on this, okay? One is it gives us practice doing trig integration, because we need that as part of solving the problem. And because, yeah, it is kind of complicated, but if you do enough of them, it's not that complicated. So anyway, we came up with the so that's the integral. Now, do we have that integral in our tables? The answer is yes. Okay, that's one of our integrals. We don't have to do any kind of fancy stuff here, and I think it's equal to, it's either negative or positive, the natural log of the absolute value of the cosine of theta. But we'll look it up here. So integral of tangent. Okay, so it's the natural log, actually the secant. Is that right? What is the integral of the tangent? I don't want to do it. Table of integrals. There we go. That's what I'm looking for. So the integral of the tangent is negative the natural log of the cosine of x. So actually, that was right. So going to our tables, this is going to be equal to negative the natural log of the absolute value of the cosine of theta. Now, to make the substitution, I need to know what the cosine of theta is from my original triangle, which I haven't done yet. So sometimes you have to go back and figure out what you need based upon the original triangle. So the cosine of theta is the adjacent over the hypotenuse. So that's the adjacent is 3, and the hypotenuse is, it's the other way around. No, yeah, that's right. Adjacent over hypotenuse. So it's 3 divided by the square root of 9 plus x squared. So if I plug that back in here, I get the negative the natural log of the absolute value of 3 divided by the square root of 9 plus x squared plus c. which, the original integral was x divided by 9 plus x squared dx. So let's see what we get if we just use u substitution. U equals 9 plus x squared, so du is equal to 2x dx, or x dx equals du divided by 2. So we can say this is 1 over u times du over 2. So you get 1/2 the integral of 1 over u du, which is 1/2 the natural log the absolute value of u, plus c. In this case, u is that, so I get 1/2 the natural log of the absolute value of 9 plus x squared plus c. And you look at the two answers and you're like, they don't look the same to me. Here I've got that. That's what I did using trig substitution. This is what I got using u substitution. So anybody know how you can prove they are the same using the properties of logarithms? Yeah, I think you could do that. I'm not sure. What if you rewrote square root of 9 plus x squared in terms of a fractional exponent? So then I'm going to convert that one into this one. So if you, so we're going to take the top one, and what we're going to do is we're going to rewrite this as 9 plus x squared to the 1/2 power. And then you can move this to the numerator, make it negative. So you'll have 3 times 9 plus x squared to the negative 1/2 power plus c. So one of the properties of logarithms is you have an exponent. Now this exponent is not applied to everything, but then you can do what Daniel said. So we could say this is the negative the natural log of 3 minus the natural log of the absolute value of 9 plus x squared to the negative 1/2 power plus c. But if you take this and add it to that, it's just another arbitrary constant c. So that part we don't have to worry about. So we're going to combine those two into another constant, and then you can take the exponent out because now the exponent is over the entire thing. So you take that outside. So you'd end up with now the argument of the natural log would just be 9 plus x squared plus my new c. And negative 1/2 times negative 1 is 1/2. So you get 1/2 the natural log the absolute value of 9 plus x squared plus c. So you do get the same answer. So they are the same answer. You just have to use the properties of logarithms to show that they are the same thing. So that's kind of an example of using the tangent. Now I'm going to show you one more using the secant. Then we'll come back and do some more. But so let me think of one that I know's, well, yeah, let's just make one up here. So let's say we have the square root of x squared minus 9 divided by, yeah, we'll do the one like we did just a minute ago. Remember we had x divided by the square root of 9 minus x squared. Now it's x squared minus 9. So that's all I've changed. So what's the answer going to be? It's going to be equal to positive the square root of x squared minus 9. That's the answer, but let's prove we can. Let's do it with trig substitution. But you have to use, because we have x squared minus 9, we can't use the tangent or the or the sine. So we're going to again make our triangle up. Flip this thing around. This is theta. So we're going to choose. We're going to use the secant. And why do we use the secant? Which the secant is hypotenuse over adjacent. And that's so that when I use the Pythagorean theorem, the third side is going to be equal to x squared minus 9. Because this squared plus that squared has to equal that squared. So if I take x squared is equal to 3 squared plus the square root of x squared minus 9 squared, that's equal to 9 plus x squared minus 9, which is x squared. Okay, so it does work. Okay, so that's my triangle now. So because I use the secant, I can say the secant of theta is the hypotenuse over the adjacent. You'll notice a trend here. You know, the original definition that we're using here is x over something, or whatever the triangle turns out to be. Okay, so so I can solve for x. X equals 3 secant theta. So there's my first substitution, just like before. So let me underline it. So this we can use that substitution. We need dx, so as usual, we take the definition for x and we take the derivative. So the derivative of the secant is secant tangent. So that's our dx substitution. And then the third substitution is this thing. And what we do is we use a trig function that involves the square root term and the constant. So that's opposite over adjacent. So that's the tangent. So we're going to say the tangent of theta is the length of the opposite side divided by the adjacent side. And so I can solve for x squared minus 9. That's equal to 3 tangent theta. Okay, so there, let me underline these again. So this substitution here will be used there. This substitution here will be used there. So we have the 3 substitutions. And we plug those in and see what we get. And we'll simplify it. So for x, we put in 3 secant theta For dx, we put in 3 secant theta tangent theta d theta. And for the square root of x squared minus 9 squared, we put in 3 tangent theta. Okay, so let's simplify. That cancels out with that. That cancels out with that. So we're left with 3 times the integral of the secant squared of theta d theta. And if we're lucky, that'll be one that's in the book, which it is. What's the integral of the secant squared? What's the derivative of the tangent? Secant squared. What's the integral of secant squared? Tangent. Okay, so the answer is tangent. So we can do that integral. So when we do this integral, you'll get 3 tangent theta plus c. And then we go back and say, okay, have we already solved for tangent, which we have, so we don't have to do any extra work. So we go back to these original lists. If it wasn't one of the trig functions that we're using, secant or tangent, we could go back and figure it out. So the tangent of theta is equal to the square root of x squared minus 9 over 3 plus c, which simplifies down to the square root of x squared minus 9 plus c, which is what we expected, just from our past experience. So those are the three methods. You just have to you basically just have to look at the original problem and look to see whether you have a squared minus u squared, a squared plus u squared minus a squared. All of these a has for all of these u has been x, but it doesn't have to be x. It could be something else. It could be if you had to complete, if you was completing the square and this part was the perfect square, then that would be u, whatever the argument of the squared part that involves the variable. And the a squared is the other part that's left over. So let's try something here. So let me get a problem that we haven't done yet. Okay, so there's tangent, secant there. We've done that one. Okay, let's do this one. So this is something we have not solved before. Because a lot of times when we have the square root, it's been the denominator. We solved the reciprocal of that, right? X over the square root of 25 minus x squared. That's just like the problem we just solved, but this is different because it's the other way around. But you'd have the same three types of substitutions. Because you have 25 minus x squared, we know we need to use the sine of theta. So I draw my triangle, and I have the sine of theta is going to be the variable part divided by the constant part. The sine is the opposite over the hypotenuse. So I make the opposite side x, the hypotenuse 5, and as a consequence of the Pythagorean theorem, the adjacent side is going to be equal to the square root of 25 minus x squared, which is what we are looking for here. So I'm going to let you look back at the first problem that we worked on. Hopefully you took reasonably good notes and get to the point where we make the substitutions and simplify it, and then we'll see what's there. So you start off, I'll give you the first step. Sine of theta is equal to x over 5. Okay. Then you're going to solve for x. Then you'll calculate dx. And then you also need to find, ultimately you need to find what the square root of 25 minus x squared is equal to. And those three substitutions you'll be able to put into there. So this one, just solve for x. Here, take the derivative. Here, use the trig function that involves, that's why I left space there. The trig function involves the ratio of the square root term to the constant term, whatever that is. It's the same as the one in the first example, isn't it? So who do you guys play next?
Rye Cove on Friday.
Rye Cove? Where are they from? Rye Cove. And what did you say it was?
On Friday.
Friday? Okay. Yeah, I saw there was one of the news stations had your game, didn't they? Yeah, which one was that? Do you remember? Yeah, because I watched the I think I actually saw it when it was actually the news. I didn't go back and look at the recording. I was like, oh, there they are. There's my girls. My math girls. Okay, so that's what I got. So you take the original definition, multiply both sides by 5, solve for x. Take the derivative. The derivative of the sine is the cosine. Add your d theta on the end. You look for the third one, you look for the square root term, which is 25 minus x squared, divided by the constant term, which is 5. Out of the triangle, you say, okay, the square root term is the adjacent side. The constant side is the hypotenuse. That's the cosine of theta. So the cosine of theta equals that. And to solve for the thing I'm trying to substitute for, I multiply both sides by 5. So I have those 3 substitutions now. So for x, I put in which is the denominator is 5 sine theta. The numerator is 5 cosine theta, and dx is 5 cosine theta d theta. So I get to that point. Now the question is how to solve that. That's not as simple. It's not just you're going to have to do something to make that work. So anybody have any thoughts what you might do? The options are you could choose if the sine were in the numerator, you might be able to use some kind of trig integration techniques. The problem is the sine is in the denominator. If it was sine over cosine squared theta, then I could let u equal cosine of theta and du would be equal to sine theta, and that would work out. But because the squared term is the numerator, it doesn't help you any. You might say, well, isn't cosine over sine cotangent? But then you have cotangent with cosine, and those don't like each other. You want to have sine and cosine, or secant a tangent, or something like that. Any other ideas? Those don't work. What is one thing that we used a lot when we did do trig integration? What identity did we use? We used the Pythagorean identity. So I think that sounds like a good idea based on my experience. So what you would do is you replace cosine squared theta with 1 minus sine squared theta. And so then the first term, so you'd have 1 over the sine of theta, and then you'd have minus the sine of theta, d theta. And 1 over the sine is the cosecant. So the second integral is easy. That's the cosine. The integral of the sine is negative the cosine. So that'd be negative the cosine theta. The first one, that's in the book. The integral of the cosecant, well, let's see, what is that? Let's look that up online. I can't. The integral of the cosecant is negative the natural log of the cosecant plus the cotangent. So the first one is going to be negative 5 times the natural log, the absolute value of the cosecant of theta plus, is it cotangent? I've already forgotten. Cosecant, so it's right here, cosecant plus cotangent. So we didn't have to use any special trig integration here. We just had to use the Pythagorean identity. Now the problem we have is that if we go back to look at our original substitution, we have the cosine of theta and the sine of theta, but we don't have the cosecant or the cotangent. So what you'd do is you'd go back here and you'd say, okay, the cotangent is going to be the adjacent over the opposite, and the adjacent side is the square root of 25 minus x squared, and the opposite is x, and the cosecant is equal to the hypotenuse over the opposite, because the sine is the opposite over the hypotenuse, so it's the opposite. So you take the hypotenuse and the opposite. So those are the additional substitutions that I need to come up with based on my original triangle. So let me just drag those over here. So there was that one, and the other one was that the cosine of theta was equal to the square root of 25 minus x squared over 5. So now I can make all these substitutions. So you get negative 5 times the natural log of the absolute value of 5 over x plus the square root of 25 minus x squared over x. These negatives cancel out. 5 times the square root of 25 minus x squared over 5 plus c. So that's the answer. You know, based on our original integral, I mean, you're like, wow, that's crazy. Because the original integral didn't look that. All it was just the reciprocal of something we've dealt with in the past. But it works. This is the answer. So it's impressive that we can do something that complicated, right? So just let's review what we did, because that one was more complicated than the one we did before. All the other ones are reasonably easy integrals. So we looked at the original integral. We said, what is the form of the square root term, if there is a square root term? It was a squared minus u squared. So that means that we should set up our triangle as a sine, the sine function. So we know that the u part has to be the opposite, and the constant part has to be the hypotenuse, so that when we use the Pythagorean theorem, the third side ends up being of the form that we want to get in the original equation, substitution. So we choose the sine of theta, we put those on our triangle, use the Pythagorean theorem to get the third side. Then we solve for x. We always solve for x. So that gives us one substitution. You take the derivative of this, so you use your derivative tables to figure out what that is if you can't remember what it is. And then the third substitution is a square root term, so we look at what trig function involves the ratio of the square root term to the constant term. The square root term is the adjacent side. The constant term, 5, is the hypotenuse. Adjacent over hypotenuse is the cosine. So we use that. Cosine equals that. We solve for the square root, substitution. We put all that stuff in there. We simplify it. And then we have a trig integral. We got to figure out how to solve that. In this case, we had to use the Pythagorean identity to replace cosine squared with sine squared. Break it up into two integrals, which once we redefined 1 over the sine is the cosecant. We had those in the book, so we looked those up in the book, and we got the answers. And then to finally rewrite the solution in terms of x instead of theta, we have to go back and look for what these trig functions are in terms of the original triangle, and then we substitute it in there. So I'm not going to assign any homework yet. I'm going to do it tomorrow. So that's it. So we'll see you in physics.